I get the chats. I never publish the chats ever. So don't feel like you can't ask questions in the chat because you don't want that information being shared. That's my caveat. Like, I don't publish those. I think it's kind of weird. So yeah, welcome everybody to the Utah Machine Learning Meetup. I'm excited that we could have so many people RSVP and we could have, we have a really awesome topic today. We've got some really good ones lined up. So glad you all could be here. We want to thank our sponsors. We're sponsored by Weave. They're providing the Google Meet with recording. I also work there, so it's really easy for me to get the recordings. Forge Foundation also sponsors us. They're a nonprofit that hosts us. We do have a Slack through them. Really great to, get on and chat. Like I said, the video will be on YouTube later, etc. It's on the Forge YouTube. On our Slack, on the Forge Slack, there is a jobs job board in the jobs channel. It's open to everybody to post jobs and or look for jobs. We get all kinds of jobs on there. Someone posted about working at a robotics company today. So it's very active. If you're looking for a job or looking to hire, I always recommend going there just because sometimes our attendance goes down. A lot of people watch the recordings because they get burned out during the day. So just putting that on the job board makes it really easy. I will share the link for Slack so anyone can join it after we get started. So feel free for that. We are always looking for speakers. Our stuff is on pay-per-call. We're always accepting speakers, all levels of speaking, first-time speakers, super experienced speakers, whatever. We love it. We love all the speakers we can get. And yes, it's at papercall.io/mluth because I misspelled Utah and I do that all the time. And so without further ado, I'm going to turn the time over. It's Milecia, right? I didn't ask you if that's how it was pronounced.
It's Milecia.
Milecia?
Mm-hmm.
I have someone at work whose name is spelled Alicia, but she's like, no, it's Alicia, and so I get confused. Milecia, it's all up to you now. We're super excited to have you speaking with us all the way from Oklahoma. Great state with nothing in it. I used to live there, so there's nothing there, but great people. So
and
it's totally food.
Mm-hmm.
Oh, great! There's good food there. So yeah, it's all up to you. Go ahead. You can present your slides or no slides or just chat, whatever you want.
All right. Let me try to pull up some slides first. Okay. Can y'all see my screen?
Yep, it's perfect.
Sweet. Let me see if I can present. But anyways, hey everybody. My name is Milecia McGregor, and I'm a developer advocate with Iterative. But I mostly work on the DVC tool, which is something that we use to just make machine learning easier in general. But that's not what I'm here to talk to y'all about today. We're going to go over convolutional neural networks because they really are just that cool. So gonna go ahead and jump right into an overview because I know how everybody is with this virtual stuff. You get burnout, so we tune in and out, and I like to let y'all know what we're doing so you can kind of pick up and listen when you get to the topic you want to hear about. But first, we'll go over a little background on neural networks. Then we'll jump into some basics of convolutional neural networks. We'll go over a few use cases for them, and we'll make a really small one in Python. And then we'll follow up with just a few key takeaways, some stuff that I hope that y'all learned today, basically. Okay, so a little background on neural networks. Basically, a neural network is just another machine learning algorithm that takes some data and we use it to make predictions. So neural nets are made of these different layers of nodes. And basically, it looks something like this. So you have your input features, some weights get assigned to them, or you assign some weights to them. Then there's a bunch of hidden layers that do things we don't get to see. And finally, we get some outputs. So that's the gist of a neural network. And typically, they take advantage of deep learning because there's more than one of these kinds of nodes present in a neural network. So a neural network is supposed to kind of replicate or imitate what our brain does. And all of these different hidden layers inside of the neural net represent basically neurons in our brains. That's what a neural net was modeled after because it was just trying to, yeah, basically imitate the way that we think. There's a lot of stuff that goes on in there that we don't particularly define. It just takes our inputs, we have some kind of value we assign to them, magic happens, and we get an output. But now that you know a little bit about neural nets, let's talk about the, I guess, the big boys of the neural nets, convolutional neural nets. The big thing about these is that there's a few things, but let's talk about convolutions first. This is what makes them so much different than a neural net. They have a completely different architecture. So a convolutional neural net, or I think they call them convnets. That sounds weird, but I'm gonna call them CNNs for this talk. And basically, they're just different layers with different dimensions. So instead of the hidden layers that are very linear in neural nets, in convolutional neural networks, you have three dimensions, which are basically the width, height, and depth of your problem. This is basically like doing some linear multiplication where we have multiple sets of weights and inputs that get filtered down into a size that we can handle and something that a computer can be more performant with, if that makes sense. But a convolution basically takes our layer and it scans through it to pick out the important features. So the convolution, let's say we have images, this will go through the image and find things like edges or large features like stripes or things that really define the overall shape of the image. And what happens here is it goes through a filter or something called a kernel, same thing. And what it does during this filter, it's basically looking to extract different features. So when we have our convolution, which is basically this filter that scans through every input. So it's scanning through every pixel in your image. And what happens is as it scans through, there's some matrix multiplication that's going on, and it sums these results into what's called a feature map. So a feature map pretty much takes the important parts out of our image and makes a smaller layer. So what happens with this smaller layer is that if you think of it like a grid, I have the picture here. So this is what a convolution is. Say that we have an image that is 5 by 5, and we want to make something that is 3 by 3 so that we can process it faster. That is what the convolution is doing for us. it's scanning through all of these different parts of our grid, and it's pulling out the features that are the most important, which is also going to bring us into what pooling is. So the pooling part of CNNs, this just filters it down even more. It gives us that it gives us a way to decrease the computational power that we need to process all of this data. That's pretty much what pooling does. So after the filter, like the convolution has been applied, it's going to go ahead and go through that filtered output and look for the most important features in that. And it's going to make an even smaller grid. So that is kind of like the essence of what makes CNNs so powerful, is they get rid of a lot of that pre-processing you have to do to get images into a shape that can be processed in a way that, you know, doesn't have your laptop fan running all the time, or without you needing to buy a bunch of GPU resources and things like that. So there are different kinds of pooling, but I got ahead of myself. Yeah, it decreases our computational power need. It gives us the most important value from the kernel that we got from our convolutional layer. And it also acts as a noise suppressant. So let's say you have a picture and there's a lot of like trees or things in the background. You're probably not interested in that when there's a car on fire in front of all of those trees. You're probably trying to pick out the car in that picture. So the max pooling layer also takes out some of those less important features in an image. And that is something else that gives us this nice pre-processing boost, so that we don't have to spend a bunch of time cleaning data or finding which features are the most dominant. Max pooling and convolutions do that for us. They extract the dominant features in images or in like computer vision problems, or my personal favorite, brain data. So if you're trying to process EEG signals, you can probably use a CNN and do some like pre-processing, you know, turn those signals into images, and then you can take advantage of using a convolutional neural net. But there are different types of CNNs. So we have the 1D, which these are usually used on like time series data. So instead of a grid, you just have like a single row that it scans through. So it gets through that data pretty fast. And then 2D CNNs are probably the most common. Like that's what we just saw a few slides back with the whole grid, and it's scanning over everything. And then 3D CNNs are where it gets really crazy. So instead of just a grid, you get an entire cube. So when the CNN is going through the convolutional layer, it's picking out a cube inside of your data or your image instead of just a square. So that, honestly, those models take a while to build because there's just so many factors to account for. But let's talk about some of the big differences between CNNs and regular neural nets. The big one that drives a lot of CNN use is just the amount of time that you can save on pre-processing data. You don't have to worry about extracting features by hand. You don't have to go through and label a lot of images. You can just, hold on, I think I got a question. Oh, no, no question yet. But you can just depend on the convolutions and the max pooling layers to filter down to those important features that you'll need to classify images. And then this is something that is huge. So CNNs learn what characteristics in the filter are the most important. And what that means is, for example, say that you have an image of a person riding a horse. It doesn't really matter what the background is there when you're just trying to identify person and horse. So as it goes through these different filtering layers and you get rid of more and more of those parts of the image that just don't add any value for classification, you're left with only the parts that matter. So if you think about the way that we see things in context, which is also something that CNNs do really well. They are, what's the word? Spatially and temporally sensitive. So they take into account what the data was before the convolution and what the data is after to get an idea of what exactly it's looking at. So what we're doing is taking a lot of the, I guess, manual labor part out of it. When we use a convolutional neural net, it does pretty much everything for us. There are a few things that we have to define, like with the hyperparameters, you have to decide on your filter size. So if I go back here real quick, like this filter is a 3x3x1 because it's a 3x3 grid and it only has a depth of 1 because, oh, did somebody unmute?
I did. So I do have a little bit of a question when it comes to max pooling.
Mm-hmm.
Is that like a constriction in one of the layers in which you have less neurons leading to the next layer?
Yeah, so basically what happens throughout this whole CNN, you're trying to get from, let's say, this 5x5 down to, I don't know, like just a 2x2, for example. So in this case, the convolution is making this 3x3, but then the max pool would go into this 3x3 and pick out the specific features. So if we did want a 2x2, our max pooling would be a 2x2 grid, and it would go through all of these and pick out like what is the main point, basically. Like there's max pooling and average pooling, but really max pooling is the best of them because it just returns that max value from that portion of the image covered by the kernel produced by the convolution.
Okay.
Does that make sense? I know it's a lot of like, and then this.
I'm pretty new, so I'm still trying to learn the basics here. But yeah, that's cool. You can continue.
Okay. Feel free to just jump in with any questions. Like that is totally fine here. But I'm trying to think where did I leave off at? Somewhere in here. Oh, yeah, it was somewhere in here. So one thing that is a big difference between CNNs and neural nets is that CNNs don't perform nearly as well as neural nets if they don't have a lot of data to train off of. Since they do so much image simplification, because that's really what a CNN does, it makes a super simple image that the computer can identify for us. But when it doesn't have enough training data, the way that it picks out features can get really weird. So we're not defining things up front like we do with the neural net, or at least not as much as we do. And there's just a lot of like black box stuff happening inside of here, which I don't know if we were talking about this when anybody was on, but it's really just a lot of ridiculous math happening behind the scenes. But few use cases. So we've talked about how complex they are. We've talked about how these layers basically strip away all of the stuff from the image that we don't care about. But why would you actually care to go through all of this work? First thing, if you're familiar with the good old MNIST example, you'll know that you can use a CNN to recognize characters from different handwriting samples. And of course, there's plenty of computer vision applications, which this is one of the things that CNNs are super powerful for, just because they do process images so fast. Like, I worked on a robotics project where we were making an autonomous golf cart because, well, we couldn't afford a car, whatever. But what a CNN does is, as a camera is bringing in new data, it is taking all of that information and parsing it down to the most simple things it can. But the fact that it does it so fast, that's what gives it the edge over regular neural nets. Or if you're familiar with neural nets, what is it? Feed forward neural nets are super similar to CNNs. It's just they don't handle feature extraction as well. But that's why we use it in computer vision. It's used in banking, maybe not surprisingly, but sometimes you just need to read digits on checks because people write checks. It's how, if you've ever used mobile deposit for a check, or you've put a check into an ATM, there was probably a CNN behind that was telling the system, like, hey, this character is a 6 or a 7 or whatever. So it's a little bit how those work. And then this one is super fun and useful. If you remember, like last year, the post office slowed down, super slow, has nothing to do with neural nets. But convolutional neural nets do help the postal service read things like zip codes that we write down on envelopes, or to get addresses out of just handwritten characters. But all of this to say, CNNs are super useful and they're pretty much everywhere. Like, if there's something that uses an image for anything, there's probably a CNN somewhere lurking behind the scenes.
Could you kind of define the difference between a CNN and a neural net?
Yeah, so really the main difference between a CNN and a neural net is just the architecture of it. So with a regular neural net, it transforms inputs by just pushing it through these hidden layers that have these weights assigned to it that we don't really have anything to do with. But with a convolutional neural net, first off, the layers are three-dimensional, if that makes sense. So instead of just pushing through this one thing, like for our example, we have, let me go back to that picture because that's a good picture. But for this example, it's 3 dimensions because we have our X, Y, and then if there was some depth to it, which in our case is just 1, that would make up that 3rd dimension. So technically 3D convolutions are 4 dimensions, but I don't know how they do that. Like, I've never processed MRI data, so
Okay.
This is as deep as it goes. But there's that difference with the whole 3D thing versus 1. And then the neurons in one layer don't necessarily connect to all the neurons in the next layer. Because since we're taking out this little region, there's some stuff that's just going to get left out. Like, this edge up here probably isn't going to be over here in our convolved feature. So at the same time, it's like we get a little bit more control than we had with the regular neural net, but we do lose a little bit of information about our data throughout the whole process. But that's kind of the point, is to strip away the stuff that we don't need.
Okay, so I know don't in like neural networks, if the weight is so low for one of the connections, you can just trim that.
Yep, pretty
So
much.
does CNNs do anything similar to that? Is there any back propagation in a CNN?
Not that I'm aware of, but what CNNs do have, you typically add padding to your feature map, and that's how you try to preserve some of those parts of the data that might be valuable. Like, for example, in the first convolutional layer, you could potentially lose some of the edges of the picture, which define like the boundary of things. And if you add some padding, which is one of the hyperparameters for making a CNN, that will give you like, that'll keep you from losing that important information if you know that it's important for your problem.
Okay,
So,
yeah, that makes a lot of sense. Thanks.
mhm. Did anybody else have questions?
Hey, I got a question. What are some of the, you mentioned one of the problems you can run into is if you don't have enough data. What are some of the other pitfalls or the kind of things you need to watch out for? Or have you ever seen one that just went really wrong?
I can't say I've seen one just go like catastrophically wrong, but back propagation is one of those things that it doesn't really do well. I would say that if you kind of change the orientation of an image, that completely throws off a CNN. Like, it doesn't handle variance between images very well. And then if you're not careful with the pooling layers, which can be tricky, of course, all ML is just trial and error really, but if the max pooling layers are implemented weird or at the wrong time, or there's some padding left off at some point, you can get some some funky predictions. Like, I've seen an image of a cat get classified as a person's face. That was funny, but it wasn't a good thing. So watching out for those max pooling layers, and if you have any images that are slightly like rotated or skewed or flipped or anything, that can break the CNN pretty quickly. Did anybody else have questions? All right, so by vote of awkward silence, I will go ahead and pretend I was already on this slide and switch to share something else. So let me see if I can do that.
Code's my favorite part, so I'm really excited. I love code.
Let me see. Oh, of course, the computer wants to do something weird right now. I'm not sure why. Is it gonna let me share?
There we go.
Okay, cool. So I'll try to make that a little bit bigger.
There we go.
And sweet. So this is basically what a simple convolutional network looks like. We have our convolutional layer, first one, and this just says, hey, we have one channel, it has 8 inputs, which means it's probably like an 8x8 grid, and we want to get back this 3x3. Cool. Or maybe I have that backwards. And yeah, I had that backwards. But yeah, this is in PyTorch, so implementing it in TensorFlow would be something completely different anyways. But I just kind of wanted to show y'all that, hey, we got this convolutional layer. It has some padding to make sure we don't lose those edge features. And then we do our max pooling. And then we do another convolutional layer to get it down even more. And then down here, we start to do some linear transformations just to get the data in the right shape for the rest of it. And then here you'll see we have just an activation function because, you know, you need a nonlinear output. Then some more pooling, another nonlinear, some stuff that was particular to this little example. And this is just an MNIST example, by the way. But yeah, we just have some convolutional layers, some max pooling, fancy stuff to get the data in the right shape, a little bit more fancy with the activation layer, and then we just return the CNN in the end. But in, what is that? Like 15 lines of, 16 lines? 17 lines of code, you have a whole CNN implemented and ready to work on an MNIST data set.
So I just have a quick question, sorry. Looking at dense 1 and dense 2, I see you've downsampled from basically the flattened convolution to 32, and then from the 32 and down into the 10 MNIST classes. I'm just curious, like, what was the motivation behind using both of those linear layers? Did you just get better, like, performance using a non-linearity between the two dense layers?
That was pretty much it.
Okay.
Like, the accuracy on this just straight out of the bat is 85%. So that's basically where that came from. It's just performance thing.
Cool. Yeah, thanks.
So how many different layers are in this?
So just for the CNN itself, there are just these 3. Like, this is the CNN, everything else is some kind of cleanup. I mean, technically this is 2 because the CNNs have the activation layer, but so 1, 2, 3, do some cleanup here, and then we have the convolution activation, and another pool, more activation, just getting the view right, and more activation. So the main 3, though, are these. Did anybody else have questions?
I guess I had one more. Are you training this on CPU or on GPU right now?
Just CPU right now.
Okay. So how long does it take for you to train something like this on a CPU?
Ooh, well, for MNIST using this particular convolutional net, it probably takes, I don't know, a few minutes. Just
Okay, so it's pretty fast.
Yeah, it's pretty fast. On something more complicated, like I did an example with this voice classification where people say words and you predict which word it is. That one, even on CPU, still took maybe 10, 20 minutes.
Okay, so it's still pretty reasonable, probably just because it's a fairly small network.
Now, when you get like the big ridiculous networks, the convoluted convolutional nets, those can take days. if you're just running on a CPU. Like, I would highly recommend using the GPU if you have something bigger than this, a lot bigger than this. Or if you have some just ridiculous data, maybe you are processing MRI images. I wouldn't try to run that just on a laptop.
Cool. Yeah, thanks.
Mm-hmm. Did anybody else have questions?
See you, John. Thanks for coming. John comes like almost every month. He's super nice.
Well-
Go ahead.
What kind of data could you train this on? This small of a neural net.
Ooh. I know it's a lame answer, but it depends. So if you already have some clean data, you could probably train with a neural net this small. But if you have a lot of like cleanup to do to your data, or it's a really complex problem, like you're trying to identify 3 or 4 things in an image, this is not going to do it. But if you have something simple like handwritten digits, or you're trying to figure out if something is a cat or a dog, like real basic stuff, you can get away with something this small.
Oh, wow. Cool.
What's the training set size you would want if you're doing something simple, like is it a cat or a dog, where you'd be able to get pretty accurate, or another kind of simple problem?
I would say if you're doing some kind of like simple image classification, as long as you have at least 10,000 data points, that should be good enough for a CNN. But that is definitely on the low end. I haven't, as far as like production models, I haven't seen anybody go too much far below 10,000 images. But just to play around with, 800 to 1,000.
Okay, thanks.
Mm-hmm. Did anybody else have questions?
I was just gonna ask, in like your day-to-day work, do you work with like stuff this small, or do you end up doing like super, like, I just want to kind of get a feel for how common simple models are as compared to like the more complex ones.
Gotcha. So day-to-day is not this simple. Like day-to-day is, it might take me 2 weeks to a month to come up with a model that halfway works. So if it takes a while, that is totally normal, because you have to figure out what size you want your like layers to be. 8 and 3, those kind of came out of nowhere, but at the same time they didn't. There was a lot of like, oh, well, if my image is this size, then what happens if I put it at, like, what happens if I want to return a filter that's 3 by 3? Okay, that works. But what if my image was, I don't know, 16 by 16? 3 by 3 takes too long for a first layer. So it's just a lot of like, this feels right from what I've done in other projects, so let's start here. Okay, these results kind of suck. Let's do something else.
That makes sense.
So is a lot of your time spent finicking with the structure of the neural net, or is it gathering data? Well, what takes more time there?
Ooh, that's a rough question. A lot of times just getting data is hard. Like, getting useful data, I should say, is hard because you have to go through and make sure that the images actually make sense for your problem, or that they have, yeah, you got to make sure that the data makes sense for the problem. But getting into the model part where you're tuning hyperparameters, like, for example, with CNNs, the typical hyperparameters are the kernel size, the padding, how many filters we want to use, and what's called the stride of the filter. So a stride, if I go back to my nice little picture here. So in this case, a stride would just be like, we move this yellow grid over by one column. So these three would be highlighted. And then if we took another stride, it would be this last part. But that's where a lot of the trickiness comes in, is tuning those hyperparameters, because you really just don't know until you're working on the problem what exactly is best. There's some stuff you can use, like different heuristics and things that people say, but a lot of it is just really, really good guesswork.
All right. Thank you.
Mm-hmm. Any other questions? All right. Vote of awkward silence wins again. So let's see. Where am I? Well, now that y'all have seen a little bit of code, let me see if I can get back to my slides real quick, because, well, we're about done. So, yeah, some key takeaways for y'all today. This is something that comes up a lot in machine learning. Everybody's like, oh, what's the best algorithm? Which is the most performant? What gives you the best accuracy? Blah, blah, blah. A lot of times you have a good idea of what algorithm's going to work really well for your project or your application, but it's okay to try a couple of them out before you just commit to one. Like, a problem that I've seen happen a few times is just people get so fixated on the algorithm that they forget if it actually applies to the problem. So keep that in mind. And then take advantage of the libraries that are out here. I'm not sure why you would want to write your own convolutional neural net thing when you have PyTorch and TensorFlow and probably some other Python libraries that I don't know about. You don't have to know how to do all of that complicated math to get a CNN to work. So just use what's out there and read the docs, because they're pretty good. And then, especially with machine learning, CNNs, everything, when you get handed a machine learning problem, take the time to just break it down into multiple steps. You're going to run into some kind of bugs. There's going to be some weird accuracy issues. Maybe your accuracy decreases over time and you don't quite know why. But if you have your problem broken down into multiple steps, it'll help you figure out where the root of it is a lot faster than if you just started with some ridiculous convolutional neural net and now you're 2 days away from having to release to production and your accuracy keeps decreasing every time you train. So break those problems down before they break you down. But yeah, that's really all I have for y'all tonight. Did y'all have any other questions for me?
So I was kind of wondering if you have any like next steps for somebody trying to learn this stuff. What might be a good resource or some challenge or something somebody could do?
Ooh. I'm a
Kaggle.
big Kaggle. Always
Kaggle.
Kaggle.
How do you spell that?
Kaggle. So Kaggle is owned by Google now, but basically it's a web platform that you can go on, and they have data sets for you to try and train models against. There are also like example codes. Sometimes they run competitions. They also have lessons, and then the notebooks themselves are online. So like sometimes they even have GPU resources for you. So it's a really nice place to go get your hands dirty. And the best part is the data sets are there, and a lot of them are nice.
Yeah.
So you don't have to get you can get familiar with the machine learning and the data science of it without having to do the crappy stuff.
Yeah.
It's true. They do have a bunch of like data sets that are already labeled and they're clean, and it's just nice to be able to focus on the code.
Yeah.
But
That's the dream.
Kaggle is definitely it. Like even some of the competitions you can pair up with just random people. Like it's a pretty cool community.
Yeah. That sounds awesome. Thanks.
But I guess I'll just stop showing that slide. So yeah, did y'all have any other questions?
That was really awesome, Milecia. So we'll give 10 more minutes for questions. If not, I'll go ahead. If nobody has an immediate question, I'll go ahead and stop the recording. Is that okay? We feel good with that, stopping that recording? And then you could still ask questions. You just feel less pressure about the recording.